So now for something different. I'm going to talk about Kafka at scale. At least I think it's at scale, and also Kubernetes. So we're going to be looking at a lot of YAML and stuff that's worse than that. My name is Hans. I'm also a co-organizer of Cloud Native Copenhagen. I'm a staff software engineer at Unity. These are some of my contact info. Um, I'm just going to dim the lights a little bit, not for dramatic effect, but Unity has this nice slide template, which is all white on black, and works best in slightly subdued lighting. So we have around 40 slides, so a packed agenda. But if you have any questions or anything that isn't clear during the presentation, just let us know. I want to make sure that we capture everyone. I'm going to talk a little bit about the challenges we had with Kafka, the different solutions that are available to you, why Kafka is hard to run in Kubernetes, tell a little bit about what we call Kafka as a service. There's going to be some kind of demo as well, demo God's willing, and we'll end on some stuff we're working on currently. So how, by show of hands, how many in here have run used Kafka? Let's say that. Wow, that's a lot. Okay, I was not expecting that. It's a very popular piece of software, obviously. That I won't dwell too much on this, and this is also super information dense. But in case there's a few of you that doesn't know anything about Kafka, Kafka is a distributed system that is basically like a message log. So you write until a tail, and then someone else reads that in sequential order. It is distributed in that you write to a topic has partitions, and then one broker, so the data lives on a broker. One broker is the leader for that partition, and then others are following it. So the data is replicated for redundancies. So you always produce or write to the leader, but you can read from any follower, actually. Okay, but moving quickly on, since there are so many hands, these were some of the challenges we had running Kafka. I've been in Unity for 3.5 years, but the last 2 years or 1 year and a half, I've been working in a data team. And when I came, stuff was on fire quite a lot. And that is not good when the system you're running is responsible for $1 billion in ads revenue. So really, we had very, very low tolerance for failure, actually none at all. You could just take $1 billion per year, and then you can figure out just how much 1 minute of downtime costs. So it's super, super important. Not to mention that if you ever had any issues, one thing is the loss in revenue, but the loss in reputation would also be super bad. So at the same time, we were doing a non-trivial amount of data, like 100 petabytes per month, and we mapped it out. It's also growing exponentially, just to make matters worse. So that can really, really, really add up. But it's also what makes it fun. These are, Unity is a public company now. These are data numbers. Just a small disclaimer. You can go to our website to find the actual revenue numbers reported and everything. I didn't ask for permission, so I'm asking for forgiveness. So, but I mentioned there were some problems. Basically, we had basically weekly incidents with this. And we didn't have a lot of people, especially people who knew or had tried running Kafka at this scale, which certainly added to the complexity of it. But Kafka is very resilient. So even though there was a lot of toil on the engineers in charge of running this thing, it was actually fairly stable in terms of impact to that aforementioned revenue. But some of the problems we were having with running Kafka the way we were running it were that it was like a big cluster, a multi-tenant cluster. And that also meant that you had the noisy neighbor problem. So you would have one topic which would then suddenly double or 10x in volume, needing a configuration change. And then you had other smaller topics, maybe compacted topics, that were super important for the business, but then we're running on the same brokers, the same machines as the heavy ones, right? And so you can have issues to this small important topic resulting from a unscheduled increase in traffic for another thing. So that is obviously something we want to get out of. On top of this, it was also deployed using Ansible. Nothing wrong about Ansible, but it's not Kubernetes. Uh, and we really wanted to get rid of this noisy neighbor problem by having more clusters. But then if you have more clusters, you don't want to get into a position where you create a Jira ticket to create a cluster and have all that thing. So we wanted Kafka as a service, speaking into your talk as well. We wanted self-service provisioning. I'll just give you a quick example of what an incident looked like. So basically, whenever there was an incident with Kafka, that automatically became a support request to Confluent, and then the people who are on call basically apply whatever mitigations were given by the first line support without necessarily looking up the documentation. Who can blame them, right? They're on a burning platform, you have a vendor, you do what the support tells you. I don't blame anyone for that. But here's a neat thing. So we discovered this quite quickly after I arrived in the team. And we had one broker that was for some reason getting overloaded during peak traffic of the day. And what do? You find a bigger box. You just scale it up, right? And eventually we landed on the biggest box there was in GCP was, well, at least at that time, a 224 core machine. And here it is running at load average 117. And the reason why we got into this mess was that Kafka has this thing of a dynamic override. So you can do static config. You can also do dynamic config where you can tune things. This tunable is called in non-replica fetchers. And what the first line support didn't understand was that it's actually multiplied by the cluster size. So they thought a box with 64 cores can do 32 replica fetchers because you have more cores than fetchers. But the thing is, if you try to figure out how many threads are doing the replication, it's the cluster size minus yourself times the factor non-replica fetchers. So at this setting, it became 928 threads. So basically, this one broker was telling the rest of the cluster to go kill it. It was committing suicide, basically. All the other brokers were not running this setting. It was just applied to this one broker that then became very busy. This was also running on the fastest storage we couldn't find, and we were trying to just throw money at it, and it didn't work at all. I'm not going to go over all the different Kafka tunables. That will be a different Kafka in-depth talk, but just a quick example of kind of the situation and the landscape we were in at that time. Other important thing to know is that, and this is a little bit Google Cloud specific. We're on Google Cloud. This entire talk is a little bit Google Cloud specific. But I think that also, to some degree, makes sense because on AWS and Azure, you have managed services for Kafka, and you don't on GCP. But our entire world revolves around one thing on Google Cloud, and that is the amount of data you can write to a standard hard drive. Like, why would you ever use standard hard drives? Well, so did someone in our team think? He started just migrating everything to SSDs, except when you have a couple of petabytes of storage, that is super expensive on SSDs. So we have become really, really good at using standard storage in Google Cloud, but there is one speed limit, the speed limit of 400 that we cannot get around. So per VM or per instance, you can do 400 megabytes per second of traffic to a disk or disks, no matter the size of the disks. But you cannot do more than 400. And you have to So the way you can overcome this is you just make many brokers, right? Each can do 400. You can quickly reach gigabytes per second. That's super neat if you have the license for it. You can see where this is going. And then you also have to keep in mind that Kafka is also doing other things. So it's accepting produced traffic from the leader, but it is also a follower for other partitions. So it's 100 megabytes per second produced traffic plus the replication traffic. And then you may also be consuming or reading data from the disk at the same time. There's a lot of caches involved, but if you read all data, you can get into that. A lot of other companies do this in a different way. They have super short retention on Kafka and then offer it all to GCS or some object storage. That's obviously also something we're working on, but our use cases of it right now necessitates that we would like at least 24 hours of retention for if we need to page someone and they need to come online and fix a system, then we have time to do all of that. There are other solutions like tier storage that can also do things, but standard hard drives have a neat characteristic. They have fairly good latency. Like if you need to go hit the object storage, you can have reads of 500 milliseconds to go get the data from storage. Uh, Having it online on a hard drive kind of mitigates that. But that's why we do it. So we wanted to run Kafka on Kubernetes for some of the aforementioned reasons. And these were some of the solutions we looked at. This talk is a lot about Strimzi, which is a community operator. It's sponsored development from Red Hat. They also use it in a commercial product, but they have this Strimzi is the open source variant of that. They have some very neat features. One of them called spot sets. We'll get into that later. We did also look at the Confluent operator and the Confluent Cloud. There's you should probably evaluate all of the options. Strimzi has some pretty unique features in how it works with Kubernetes that we're going to deep dive on. I also remembered your question, like how does it compare to Confluent Operator? We looked at Confluent Operator right when it was very new. It was just reaching GA. I haven't followed up on the later developments, but there's some very fancy things you can do with Strimzi. So that was what we did. So Kafka is a super stateful workload, and as you all know, it's not always nice to run stateful workloads in Kubernetes, but it is nice to get all the Kubernetes tooling. So in order to be successful in running Kafka, you need a couple of things. When you need there's only so many configuration changes you can do dynamically. Many of them require you to do a rolling restart, but that has some additional requirements. For instance, there's one Kafka broker that is the controller, and you would like the controller to be the one you run rotate at the end of your role, because whenever there's a controller change, it can take a couple of seconds for it to elect a new one. During that time, there's a number of operations that cannot proceed. So if you just roll it normally with a search-based role, the controller can move several times depending on which broker wins the controller election. Also, whenever a controller or broker rolls, it will move its leader for its petition to another broker, come online again, and then needs to resync whatever it missed in that window of duration. So you want to have a cluster fully in sync before you roll the next one. So doing a rolling update to a Kafka is not complicated, and in a VM world, it's also fairly easy to automate. But it is something that doesn't fit well with Kubernetes. And finally, the last thing is a network segment. We're going to be talking a lot about network stuff, but the Kafka clients need to be able to connect directly to each broker, and if the broker is apart, that can become difficult if you're trying to connect outside workloads to Kafka. So this is how it's done normally. You see other systems doing this as well. This was also what Strimzi used to do until mid last year, which you just use a stateful set, as you would often do for running stateful workloads in Kubernetes. And then you set pod disruption budgets. So you roll one broker at a time. And that's a fine solution to begin with, but it doesn't really tend to the having to roll it in a specific order, or that a pod can be ready, but you're not ready for rolling the next one. At least you might not be, especially if you have slow hard drives compared to SSDs. Then there are things like if you want to add on to your cluster, you can really only do it at the tail of a stateful set. You cannot check out a middle broker and swap it around with different hardware or scale it out, etc. Yeah. So Strimzi has developed this thing called Strimzi pod sets, and they are super smart. So normally in a stateful set, if a pod dies or has some kind of issue, it's the stateful set controller that is responsible for replacing that pod with a new one. So Kubernetes is always in control of your resources. With Strimzi pod set, Strimzi becomes that controller. So Strimzi has a lot more responsibilities then. But the thing you obtain is Strimzi now is full control over like which order to run roll brokers, and it's also fully able to ensure that the cluster is stable between each row. So I think this is pretty vital for running Kafka on Kubernetes, especially having done so in production now for over a year. We didn't have this in the beginning, and we definitely saw some issues running like rolling releases or changes. But this has really like eliminated all of those issues. So speaking into the Kafka network stuff, if you deploy a Kafka cluster onto Kubernetes, you will find that you have a really hard time connecting to it. You can connect to it from within the cluster because Kubernetes has this basic contract of every pod must be able to talk to every other pod, not pending network policies and stuff. But how do you connect to a pod from your local laptop? That's maybe not so easy, or from a different service in a different cluster or something. And for that, you need some way to open up your network stack so you can talk directly to a pod, basically. Which is can become quite messy, but we're going to explore a lot of different ways of solving that issue. This example uses node ports, so Strimzi configures a service per pod. That service is a type node port. It has a port on every node. The same old thing if you are familiar with node ports. I guess many of you are to some degree. But node ports have some issues. You get a random port in the range, and you can pre-select the port, but then it has to be unique. And we run many Kafka clusters. I think we are more than 20. And it will be really hard to manage this. Like who gets used port 30,001, right? It has to be unique. So that becomes unmanageable pretty quickly. Then there's some issues with propagating DNS changes and whatnot. Okay, so if node ports are not good, maybe you can do load balancers then. But the thing is, now you have hundreds of load balancers. They are also not free. You also have quotas on it. And if you want to run many clusters with many brokers, especially because of the hard drive thing, that also becomes completely unmanageable. But basically, it's the same thing. They create a load balancer per service, and then per service per pod, and then you have n plus one load balancers for n brokers for each cluster. Okay, so the last Strimzi supported option is using ingresses, in particular in the Nginx community ingress from Kubernetes. They can do things like TLS pass-through. So ingresses are typically what you use for HTTP services, but you can use it for like layer 4 or a little bit above for TLS. So this is also supported out of the box, but it has some other on the slides. And speaking of pros and cons, a quick summary of the different options you have available to you to access Kafka. You can use the node ports, they have super good performance, but then have other difficulties. Also, your security or compliance department might not like you opening up thousands and thousands of somewhat unknown ports, right? Randomly assigned port numbers and stuff. It's easier for them to deal with one port going and having clear ownership as well. Load balancers are good for performance, but then they also cost a bunch, and there's a limit on GCP at least. Ingresses are neat in that you have one load balancer, but then you also have to keep in mind that when you're adding in an Nginx controller, you need to scale that accordingly to your Kafka cluster. And it's like one hub for the load balancer, one hub for the Nginx controller, and then to the broker. So you also risk adding latency to your Kafka cluster. So these are all, I wouldn't say horrible options, suboptimal options, but this is what we have to deal with when we're running Kafka in Kubernetes, and this is what makes it really, really hard. We have a bit of a special solution for this that I'm going to show you later. Teaser. So what is it that we built? Well, we're just using Strimzi, which is fairly easy, but then keeping with those abstractions that the developers don't want to deal with, we are then running a lot of templates on top of that. So you give a very basic syntax, and then we build in a lot of best practices and tie it into our telemetry stack, and you get all of these things for free that the developer don't have to worry about. Strimzi does the heavy lifting along with some other components, but these are the characteristics of what we call our Kafka as a service platform. I swear we didn't sync up on these slides, but it's very much speaking into your talk as well. But yeah, it's you can self-service a cluster. We're gonna deploy one later. It's on GKE. It takes around 7 minutes, give or take. It needs to do a lot of network things. And we've been running that for a year. This is the contract. This is what you give our tool. You give it something that looks like a custom resource, and then you specify a few things, like which environment, region, how many brokers do you need, how much storage do you need, what topics, what users, etc. Then we take this and expand it onto a whole lot of Kubernetes resources underneath. But this is the simplified abstraction that our users give us, and we work with them to validate the configuration and stuff. So I mentioned there's a lot of stuff coming on underneath. We take this custom resource, and then they commit it on a pull request in GitHub. We have something of a GitHub flow. Have some GitHub experts here in the audience. I'm not sure they would agree necessarily, but it is picked up by Argo CD, which is not Flux, and and it's then of course instantiated Kubernetes resources and custom resources on GKE, and then there's two parts that does the heavy lifting. One is Strimzi. You all know what Strimzi is now. The other is the Google config connector. Basically allows us to provision load balancers, DNS records, etc., via Kubernetes resources. So it's like what is it called, cross-plane, but GCP specific. I don't know if we build it today, maybe we will use cross-plane instead. But yeah, so far this has been very focused on TCP, and it's been working quite well for us. So we use something called JSONet to actually implement this, and it's kind of in lieu of a real operator. We give this simplified input to a big JSONet engine, and JSONet, I'm assuming most of you don't know. I may be totally wrong here, but JSONet is kind of like JSON and Python combined, which sounds completely insane. And the learning curve is also horrible. But when you have mastered it, you can do some really fancy things. It's like learning regex. Learning curve is also completely horrible, but you can really do magic stuff with it. Google recommends it a lot. That obviously appeals to Google fanboys like myself. Um, this is a very quick example of something you can do with JSON. You have a person one definition, and then you on person two, you take person one, but then you kind of patch or change a single field, and then when you render it, you get the two concrete instances. Is it readable? Don't worry, it's going to be a lot worse than a slide or two. Yeah. I'm going to share the slides afterwards, so don't worry if something, or do ask questions as well if you have any questions. This is an example of what you can do with JSON, and I know this, if you haven't seen it before, it can be a little bit daunting, but in JSON, you can do things with config maps that are quite hard to do in other configuration templating languages, whatever you want to call it. So you see you have a function that takes a domain as a default value. That's necessarily that important. Then you have a structure that is actually going to be put into a config map later. But it looks just like all the other things in JSON. It's a normal object or dictionary. And then you use a variable in there. And then at the very end, we instantiate a config map with YAML in it. So Arnholm can read it. But the variable is all the way inside of the normal struct. So I don't know how you would do this in Helm, but and this might look horrible to you if you haven't seen it before, but I promise you it can become a beautiful thing later on. Now we're getting into the real meat of the Sonnet things. This is a shortened version of what actually happens underneath. Don't worry, I'll point a little bit. But you have the YAML files in the very top that are imported and then passed from YAML. And then, it's also a little bit hard to read. And then we instantiate Argo CD applications. So we take the YAML input, and then the YAML inputs that we saw in the beginning what the user contract is, becomes Argo applications. And then Argo CD knows how to render Helm stuff and YAML and JSON and JSONet. So Argo has full support for JSONet. So we can load in a library that we wrote to then render a ton of resources based on these inputs. Yeah, and then in the very end, if you know Python, this will look kind of like Python, where you have a dictionary comprehension of basically just mapping over it. So we're giving it a list of the clusters, and then we're applying a function to each cluster from the list. So if you ever want to try to mimic what we do, this is the key you need. Okay, I already arrived at the demo. So let's see if the demo guards are with me. I'm just gonna, to make this real quick, I'll just copy another example, and then we'll go over it. Clusters, demo 1. And this is the nice contract for the user. I'll just do a quick replace. Just like to point out that you just specify the name. I would like this cluster deployed in EU or West. I need 3 replicas, and these are some fairly basic options. I need to specify the storage. And if I don't specify the storage, this is kind of, we also do input validation on this. So JSON will tell you didn't specify the storage. This is kind of the minimal thing you need to specify. We need some kind of instruction on how much storage you need. And then it does a lot of other fancy things. It configures the ingresses, but then it also has a topic definition. I'll just have a single topic called my topic, and I have a user called test user. So yes, you can. And depending on how you configure it, you can even shrink it as well, but only under certain circumstances. It can do whatever the cloud can do, right? Google, you can basically only expand storage, but if you have multiple hard drives, you can remove some of them to kind of make it smaller. Oops. I need to what? Clean up? Oh yeah, yeah. Sorry for all the mess. Which also tells me I have 44 uncommitted changes. So maybe someone is already approving things, but for this demo, I have disabled branch protection, so we can actually also just merge it. We do need to wait for GitHub action to run. This GitHub action is in charge of updating a map of all the clusters. Well, thank you, Oscar. And luckily, it didn't invalidate his approval. That's neat. Just so when this thing goes into main, and you can configure Argo in so many ways. This is not Argo talk, but and when this goes into main, you get a webhook sent to Argo, and it creates an app for me, a demo 1 test. It has a ton of stuff it wants to deploy. That's also why it takes a moment. I'll click the sync button. Not very GitOps like, but you can customize this in so many ways. What it's actually going to do is going to create a ton of things. It's going to create the Kafka topic, the Kafka cluster itself. It's going to create a compute address, backend, a lot of load balancers things. It's going to configure a certificate, a TLS certificate for it. And some of these things, they take a little bit of time. So that's why it can, depending on time, I'll either have to come back or we can also just watch it. Yeah, that's what we get to talk about during the because if you have super keen eyes, you will see there's some ingress pods being spun up, and these are very special, and I'll tell you why. We'll let this run, even though I sometimes think that is cheating a little bit, but I also don't want you staring at a spinner for 7 minutes. And then we'll get back to the slide. So I mentioned there was 3 options for accessing Kafka. We have kind of added a 4th. We really like, I really like Envoy. Envoy is used as a data plane in Istio, the service mesh, and it's super performant. And it also has some pretty advanced capabilities. Not all of which we use. For the purpose of this talk, what you should come out of this with is that Envoy is kind of neat in that it has a filter for Kafka, so it actually can understand the Kafka protocol. It's one of the only load balancers that can. We just use this filter, which is just a network filter, but you can also get a mesh filter. It's set up in a very safe way. It understands Kafka 3.4, so it's completely up to date. But if it ever receives a message it doesn't understand, it just forwards it as is. So it cannot really, it doesn't mutate your messages or will fail in some way. It will just then kind of dumb down to a layer 4 proxy. But it will give you a ton of telemetry from Kafka because it understands the protocol. We use this to build a Kafka load balancer or proxy. And we need 2 things in addition to this filter. We need to know to what broker you are communicating or wanting to communicate. And then we need to know the pod IPs at all times. The example on the right is super verbose, but if you know Envoy, then it will maybe make sense. But basically, you have a listener you're listening to, and then you have a filter, and we add in the Kafka filter. then you have a cluster and an endpoint where you send the traffic somewhere. So basically, it looks a little bit like this. You get a TLS connection in, and then we look at the TLS headers. We find the SNI header. So when you go into google.com and your web browser, the browser actually tells Google, I'm looking for the TLS certificate for google.com. Now here it's saying, I'm looking for the TLS certificate for broker 00, and we can use that information to figure out where we're going to send the data. So when you connect to it to the load balancer, you just connect to one IP. You don't know where the thing's going unless you inspect the headers. Then we need to know the part IPs for all the brokers, and for this we communicate with Istio. That is then communicating with the Kubernetes API service, which is a very long way to say that we are not using any DNS-based lookups. So if a pod moves from one machine to another, therefore gets a new pod IP, we know immediately that it's new location because it's all event-based. Nothing is pulling updates. Where is this pod? Where's the cluster? This is all being pushed from the Kubernetes API service to Istio to Arnholm. Not to say that you couldn't do it in a different way, but that's how we're doing it. So there's another neat trick for reference purposes mostly, in that we're running our own Envoy using a contributed image with all the fancy bells and whistles of the service mesh removed, just simple as possible for performance and latency. And we join it into the service mesh of Istio by a very hackish way where we are setting a node ID that is compatible with Istio. But that means we can use the Istio custom resources to direct traffic. So each broker gets a service entry. It just basically tells you, hey, Envoy, if you get a connection to this host name, send it to the pod with this name, right? I've seen some nods. I know this is advanced stuff. This is some advanced stuff. I promise I'll get back to you if there's anything. So why would we ever do this sort of thing, or even attempt it, right? It's because our Kafka as a service needs to be able to communicate in many different scenarios, 4 to be precise. We have a big shared VPC. It's pretty easy to handle that, and we can just do node ports. Maybe security wouldn't be so happy, but you can get nice other things like service account-based firewall rules, and things could be done. But then we also have laptops somewhere that needs to be able to talk to a test environment maybe, or we have other services that are connected to the VPC, but not part of it the same way that things are on the VPC. And that would be very hard with node ports. You would not be able to open a firewall rule that would be close enough or narrow enough. Then we have other VPCs that are not part of the VPC. So basically someone else provision something in Google Cloud and they're not connected to the same network. In AWS or Azure, you have something called private link that you can kind of connect VPCs. You do have that in GCP, but we never got it to work at our scale. Google is still working on that. And then we also have some our own data centers or other clouds where we also would like to be able to connect to Kafka from basically the internet. There, we of course, have additional security requirements like mutual TLS and stuff. And this is all implemented on our Envoy-based proxy. Envoy can do mutual TLS, and it's very good at all these things. Google has something called a TCP load balancer, basically a layer 4 proxy on the edge with an anycasted IP address. So like HTTP, but layer 4 TCP. And we use this as well. So I think enough time has passed that we should probably check out how our little demo is doing. We have all the pods running. Oh no. Maybe it's just slow. Okay, probably Chrome paused the tab when I wasn't looking at it. Here goes me not looking at things. So I'll go somewhere else. And then let's see if my terminal history or shell history can actually help me out, because I'm definitely not going to be able to do this without it. So Strimzi has automatically provisioned a user for me and has generated a password. Oh, I'm sorry, it's already in. And I need to go grab the password. Obviously, this can be integrated with Vault and other secret management systems. So here we have a password, and then I'll make this bigger. Let's try to connect to the cluster. So first I'm going to connect a Kafka. I'm using, there's so many different ways you can talk to Kafka. I'm using the scripts, the console consumers and producers, because these will be available everywhere. I'm going to try to connect a, that's fine, warning. Doesn't look fine, but it is fine. Sorry. Oh, I can delete it. Oh. So here we have two-way communication going on. So it works. It's this is deployed on a TCP load balancer. So if you're fast enough to spot the password, you can actually talk to it. Don't worry, I'll tear it down later. We also deploy some kind of dashboard. It's super neat for, not Backstage. Super neat for users to have a graphical interface as well. This is an open source project. It used to be called Cowl, now it's purchased by Red Panda, but it's the basic thing. So here you have a view of our cluster, you have our topic, and you can see all my typos. And yeah. Oh, I'm doing a time. So this is all very neat, but not all is fine when you actually start using it. One of the things that we would like to do something about is our cost of running these clusters. If you're used to buying licensed software, this amount may not scare you, but you can see that sorry, I had to obscure all the numbers because of NDAs with Google, but we pay the same amount for our network load balancer as we do for storage, which is obviously not great. You can also see that basically storage is our entire cost. We become quite good at running Kafka as a program. It doesn't use a ton of heap memory. It uses all this memory for caching. Performance is pretty good, actually. It's the most well-behaved Java program I've ever seen. If you don't, kill it in threads and do nasty things to it. So if you take a 1 gigabyte per second cluster, which is used to be a very big cluster, now it's kind of a medium-sized cluster, and then you just multiply it by the list price for network load balancers, it gets around $21,000 per month. So that's not great. We are still either using a network load balancer, so this is like an internal layer 4 network balancer, or we're using TCP proxies or some kind of way, because if you remember all the way back to the Ingress slides, we have all of these Ingress pods, and they know how to connect to the pods, but then we need to get traffic to them somehow. So we need to expose them on the network side. We would like to do something else, and that's what I'm kind of currently working on, which is to move the load balancers outside the cluster and not use the Istio hack. So configure them using the service discovery methods in Envoy. There's a cool person on the internet who made this thing, EK Glue, which is kind of the non-hacky way of doing what I did. I just hacked it into Istio, but this is actually the proper way to do it. And if we implement this, we can take the entire cost of the load balancer and just remove it, because VM to VM traffic is free, but anything you send through a load balancer is costly. This is a well, this is a very neat thing to implement. Yeah, and yes, the demo did work. This was all I have. Yeah. Right. No class. With this amount of manifests and Sonnet and network things, there must be questions.
Lou. I have no experience and no idea what it's like to run Kafka at the scale that Unity's probably running at. I'm in my current job where we have one single cluster in AWS MSK where we put everything through. Um, so how often are you needing to create new clusters, and when is it that you decide to create a new cluster? And how many clusters are you generally operating?
That's a very good question, and it's that's also the thing we get asked the most from our users, is that they're used to having this big cluster where everything is, and now we're saying that they have to kind of have smaller clusters due to this noisy neighbor problem. And how do they figure out how many clusters, what can possibly live together? How do I connect to something or figure out where the cluster is? Um, so there's no like the answer is it kind of it depends, which is a super annoying answer. But the when we have traffic above a certain volume, we would like to put it on its own cluster. So if you do more than a gigabyte per second, we probably would like it on its own cluster. The biggest clusters we have do 10 gigabytes per second, and that's on like 80 or 100 brokers. We would also like to keep the total amount of brokers not a lot above 100, because that's at least the kind of the rule of thumb for Kafka operations. Um, so we have so that's one answer. When you have very high amounts of data, you get your own cluster. But then there's another answer, is that you remember that we have those 4 different connectivity issues, or it's not issues, cases. So some our users, they have very strict requirements on being able to communicate over the internet, but have mutual TLS and stuff. So we have some clusters that are configured in a very different way to enable that use case. So if you have very special requirements, especially network requirements, you get your own cluster. If you have a non-critical workload, let's say you have a analytical workload, so you are a lot of what we do is receive telemetry from client devices, phones all over the world, billions of devices. And if you are receiving telemetry, if you lose 1% of the telemetry, it probably doesn't invalidate all of your reports and as results of that. But if you're receiving revenue data, then you don't want to lose even a single percent. So we don't like to mix critical revenue workloads where we need to get all the data with non-critical workloads where you can actually accept a certain amount of data loss. Those clusters are also configured differently with, with retention and partitions and stuff. So it's based on the use case and also to some degree based on the amount of data. So it all depends. But it is a little bit daunting. Like Kafka has so many moving pieces, and it is a little bit hard to operate it. And if I had MSK on Google Cloud, we would probably just use that, and I would do something else. Did that answer your question?
Yeah, first of all, awesome presentation. So thank you for that.
Thank you.
I have many questions, but I have to drive back to Jutland, so I have to just ask probably one that is going to be a bit important for me. So what you showed considerations for different vendors and then the flavors of Kafka. Was Apache Pulsar at all on the table at that time? Okay, but why? Maybe you could say why.
There's so many tools in the Apache toolbox. Apache Pulsar, does that have Kafka protocol support as well?
You can run Kafka on Pulsar, yes.
Okay. So then the answer is I wasn't aware of it at
Okay.
that time.
Fair enough. Thanks.
But now I'm going to look it up. Thanks for that.
No problem.
We also use DCP PubSub, and Google Cloud has PubSub Lite, which is very similar to Kafka, but it is not Kafka. And if you have an application that is built to use Kafka and the Kafka protocol, or uses things like compacted topics, it's hard to just migrate to PubSub.
Thank you. How do you migrate from your centralized cluster into these? Do you do it without data loss? And also, if you recreate your Kubernetes cluster?
Super good question. I should probably have covered that in the slides as well. So Strimzi, in addition to running Kafka, can actually also run other Kafka auxiliary services. One of them being the Mirror Maker, which is in Mirror Maker 2 now, and it's used to mirror traffic between Kafka clusters. So we can actually get Strimzi to run a mirror of all the data. So you can do it both ways. You can move the producer first and mirror it back to the old one, and then or you can do the reverse as well. That's basically how we do it. It depends a little bit on the workload. If you control both the consumer and the producer, you can just take the producer, point it at a new cluster, and then when the consumer has read all the data, you just point it at the new cluster as well. That's by far the easiest, but not always is that available to you. And then if you need to replicate the traffic, we use Mirror Maker. You can actually also run something called Kafka Connect for all of you Kafka knowledgeable people here, which is kind of connecting Kafka to webhooks and GCS storage and other things, but has some scalability issues. That's another talk. Yeah. Okay.
You talked about Red Panda.
If I can talk about Red Panda, yes, I can talk about Red Panda. Red Panda is a piece of software that is has Kafka protocol. Most of the important API services covered, not necessarily all of it. There's still, I think, transactions is very new. It's written in C++, and they claim that it's vastly superior to any JVM program. I would tend to agree, but we really don't have issues with the JVM in Kafka. Kafka is super well behaved. They claim very, very good latency due to the fact that they don't have a garbage collector and stuff running. So it's interesting, and it's something we are looking at as well. But I think in my honest personal opinion, is that they have some very bold marketing claims, and I'm looking forward to investigating the real life workloads. I think that's fair to say. Right? Did that answer your question? Do you have any specific questions on Red Panda? It's all good. Any other ones?
Sorry, but you just mentioned Kafka Connect and some scalability issues. Do you use that, or have you stayed around it because of the scalability issues?
So we don't personally run Kafka Connect. We have written some software that does specialize for what we do. So I work in the data team. We actually take the data from Kafka, put it onto GCS, put it onto BigQuery, and do a lot of operations on it. So we're kind of responsible for taking the data from the ingestion to the data store, or data lake, or lake house, or whatever you want to call it. You could use Kafka Connect for this, but so far our attempts at doing that at scale has not really worked out. It really depends a lot on the connectors you have in Kafka Connect. Kafka Connect is kind of a abstraction on top of Kafka itself and Kafka streams, and it has some very nice capabilities, but we haven't been able to run it at like 10 gigabytes per second. So this is me showing off a little bit, but and maybe someone more knowledgeable about Kafka Connect could do that. We just haven't been able to. Have you tried it? Is- Yeah, but it's neat, right? It's the promise is very neat.
Hi, thanks for the presentation first. I noticed that you were using Confluent somewhere, Confluent images. So did you consider using Confluent Control Center in the replicator instead of Mirror Maker and the open source Scout project?
I think we used to run Confluent, and we offboarded ourselves from it a year ago to use open source Kafka. One of the reasons being that we could have any topology that we wanted. So we really wanted to have many brokers, and to do that very cheaply is not as compatible with the license model of Confluent. Mirror Maker 1 has a not so great reputation, but Mirror Maker 2 has been working quite well for us. Sometimes you also just write some, like we're all software developers, so you often just write some Go code to connect to Kafka and do things with it instead of running these more managed services. So the quick answer is no, we haven't used that at scale. I don't know how it is to run that, but I also haven't found a reason to at this point.
How big is your data team?
How big? How many are we? 11? Yeah, something around 11.
Okay.
Yeah, fairly small, I would say.
For the data you're handling, yes.
Yeah. Then there's other, the org chart is pretty complicated and moving all the time, but we only take care of the ingestion and putting the data onto a data lake. And then someone else mutates it and aggregates it and build data science on top of it. So
I have similar setup.
yeah. Okay.
We use conferences, but it's because our team covers both Kubernetes and Kafka. So we like to pay others when we cannot hire.
And that is super fine. They also have some pretty good stuff.
It's not like it's important. Actually, we're running out of time, and I only have thank you so much, Hans, and it's super nice.